So some functions don't look like they're u-substitutions, but it turns out they're exactly the right technique for this trick. So let's look at a whole family of antiderivatives that we don't yet know how to do. Let's start with our trig functions that we don't know. So we know how to find the antiderivative of sine and of cosine, right? The derivative of sine is cosine. The derivative of cosine is negative sine. So we have the antiderivatives. What we don't know is what do we do for tangent? Tangent doesn't look like a u-substitution, but it is. Because tangent is sine over cosine, we're going to set up a u-sub. So we're going to integrate sine of x over cosine of x dx. This is secretly what tangent is. And now we have to choose what is going to be our u. Now remember, the way we choose what the u is, we have to ask, what is the du? What is the derivative looking like? I had a short intermission there because I got a call from my daughter, but I will get back into our video. So we are trying to set up the u-substitution, and we notice that either sine or cosine could be a u. But what we're really wanting to know is what is du going to be? What is the derivative? And we notice that sine x dx is a nice looking derivative for cosine. So if we let u be the cosine of x, then du can be negative the sine of x dx, which means sine of x dx we can replace by negative du. And so if I put my negative on front, this is the negative that's from right there. Sine of x dx then is just du. And over cosine of x is just u. And once again, we have something that looks like our favorite antiderivative at this point, the natural log. So this is negative the natural log of the absolute value of u, plus constant, don't forget to add the plus c. And we just have to back substitute. U was cosine, and so this becomes negative the natural log of the absolute value of the cosine of x plus c. So this one was pretty straightforward. I would like you to try on your own to do the antiderivative for cotangent. It's very similar, but because cotangent is cosine over sine, you're going to have to switch what your substitutions are. So give it a try. And I'm going to show you probably the trickiest one of all the trig functions, and then let you try the other. So the last one I'm going to do on this video is the antiderivative of secant x. Secant x is super tricky because it's 1 over cosine. And when you do 1 over cosine, there's no du that appears. There's no derivative there. So we're going to have to artificially force a derivative to appear. We're not going to change it to cosine. We're going to leave it at secant. But the trick is we're going to multiply secant by the number 1 written in a really weird way. Now, in the entire history of all of mathematics, there's only ever been 2 tricks ever made to change an algebraic expression. Either you multiply by 1 or you add 0. That's it, nothing else. So this is one of those tricks. We're going to write 1 as secant x plus tangent x over secant x plus tangent x. And you're going to say, oh, no, this looks nasty. It's just a trick. You just need to know that this is the trick you need, and everything's going to work out. Let me show you. Let's plug it in. We're going to multiply secant x by this. So we're going to have secant x multiplied by fraction secant x plus tangent x over secant x plus tangent x dx. So we haven't changed the expression at all. Sorry, this is just leftovers. We're still just doing the antiderivative of secant x, but we've changed how it looks by multiplying by this ugly version of 1. Now we're going to multiply through. Remember, when you're multiplying a fraction by a number, you just multiply to the numerator. So this is the integral of secant squared of x. The secant applies to the secant, and then the secant applies to the tangent. Plus secant x tangent x, all divided by secant x plus tangent x dx. And now this looks super impossible because it's even more complicated and more ugly. But remember, we have our tool of derivatives that we remember from Calc 1. And you'll notice that the derivative of secant x is secant x tangent x. And the derivative of tangent x is secant squared x. And so my numerator right now is exactly the derivative of my denominator. So that sets up our u substitution. Let u be secant x plus tangent x. Then du is secant x tangent x plus secant squared of x dx. And so my whole numerator is just du, and my denominator is just u. So this is just the integral of du over u. This feels like it's what we're setting up every time. I promise it's not always this, but this does show up a lot. And so once again, the antiderivative is the natural log of absolute value of u plus c. And now we back substitute u to be secant x plus tangent x. So this is the natural log of secant x plus tangent x plus c. And that is the derivative, the antiderivative of secant x. So that is all for this technique, and I'll see you in the next video.